next. So level curves. Okay, so surfaces and well, every surface could be described as generating circles, generating ellipses, generating parabolas, depending on what kind of surface we generate. Alright, so again, these surfaces are three-dimensional objects in which again we go X, Y, and then Z. Now, however, suppose we'll look at these surfaces from a bird's eye view, from top to bottom. We can imagine this, like for example, this cone right here being generated by circles, So if we focus, for example, on the center, in this case, the cusp of the cone right here, so we can trace a circle, and then another circle, and then another circle, and then generate the solid. In this case, generate a cone. In this case, it looks like a circular cone. Although more general, it's called elliptic cone because, well, depending on whether the coefficients A, B, and C are the same, well, that's going to be a circular cone rather. All right. And you have seen this before, well, number one, by the way, these circles, for example, let me take as an example the second concentric circle, which is for k equals to 2. Notice that the value of z, the height, it's always the same regardless of where you are surrounding the surface. And well, where have you seen this before? You might have seen this in these maps when you're looking at news, the weather, how it's going to be. These maps are called isothermals, and well, we have different colors that represent the different temperatures. They're labeled, so like from green to red, they go hotter, and below they go colder. But what are these lines? These lines right here, these curves, are points in the map in which the temperature is exactly the same. And then that's why they're called isothermals. The iso, same, thermals, temperature. Okay? Those of you who are engineering majors, chemistry majors, so sooner or later you're going to take this class about thermodynamics, either as a thermodynamics itself or physical chemistry, in which you will look at these kind of maps, in which, well, again, each color represents a change in the temperature, but these lines or curves rather are points on the map in which the temperature is the same. And related to the graph right here, all these points are the same height. There's other maps, actually, not just the isothermals, so we can, well, I don't have another map, but maps that represent, for example, not temperature, but rather height. When you want to go hiking, you want to look for places where it's the heights are not, or rather the changes in the height are not too steep, or depending on the height you are, so that's the purpose of these maps, to give an idea of how high you're gonna be in a mountain or in a route when you're hiking. And well, this is of course described by functions, but of course, those functions are not going to be something like x squared plus y squared equals z. Those are more elaborate functions. But I think this was a good way to relate what we're going to do here with something you may have seen before. So, given a function z equals to f of x, y equals to 6 minus 2x minus 3y, sketch the level curves for different values of k, 0, 4, and 8. And that's how we're going to create like a map for different values of k. So what we do in this case is we will replace the variable z in this case with the different values of k. For example, for k equals to 0, we're going to get 0 equals to 6 minus 2x minus 3y. And in this case, solving the equations, having all the variable terms on the left hand side, that's 2x minus 3y, or rather plus, equals to 6. Okay, so what kind of equation is this? So we're no longer looking at the surface. Now we have two variables, x and y. So we're looking at curves in this case. So which one is this in particular? So as a hint, well, notice the powers of x and y are to the first power. So just lines, right? Just lines for which, okay, let me solve for y in this case only. So that's 3y equals 6 minus 2x, and y equals to negative 2/3 x and plus 2. So we're going to get this line right here. 3, 4, 5. So we're going to have a line at the y with a y-intercept at 2 and a slope of negative 2/3. That is negative. So go down to units and run 3 units. That is to go down to, and that's going to be our line. All right. Let's do this for k equals to, how did we say 4, right? So for k equals to 4, we get 4 equals to 6 minus 2x plus minus 3y. And 4 minus 6, that's a negative 2, equals to negative 2x minus 3y. And in this case, you might want to just write this, change the signs of everything. That should give us 2x plus 3y equals to negative 2. Alright, so that's going to give us, okay, did I do a silly mistake here? Looks like I did, yes. Okay, never mind. That's fine. So this time we're going to have the equation 3y equals to negative 2 minus 2x, and y equals negative 2/3 x. What is this going to be? Minus 2/3. So we're going to have a different line over here. I'm going to use a different color. So negative 2/3, that's the y-intercept. We're going to have this line, and it in fact has the same slope, negative 2/3. So that's another line. All right. And for the last value of k, okay, make some space here. For k equals to 8, this is going to be 8 equals to 6 minus 2x minus 3y. That's going to give us a 2. That's a 2 equals to negative 2x minus 3y, which essentially is going to be, well, number 1, 2x plus 3y equals to negative 2. I'm going to solve for y again. That's a 3y minus 2x equals to negative 2x minus 2. And y equals to, wait a minute, am I getting the same result? So right here, what happened? So 4, this one? Yes. Yes, right? All right. So then it should have been instead not here, but I can spot the mistake. I know I did a mistake. So that's 2/3, which is somewhere here, and the same slope. Over here, that's going to be y equals to negative 2/3. Bless you. And minus 2/3. And yes, that's the 1. That's going to go down over here. So So in this case, well, this one is not that interesting, but we start with something simple like this so we can get the whole gist of how we create different level curves. Well, because this is a line, so essentially what we have is, so if we consider this our 3D, in 3D, we would have something like this with one plane and then another plane and then another plane. We would have 3 planes, well, at least for these 3 values of k, but we would have, of course, we can have more planes if we did these different level curves, or rather level lines, for more values of k. The next one will be for sure more interesting to create. So we have the function z equals f of x y equals to x squared plus y squared, and sketch the level curves for c equals to 0, c equals to 4, and c equals to 9. So in this case, well, I'm using a different letter. You can use k, you can use c, so it doesn't matter. So let's see. For c equals to 0. For c equals to 0, we're going to have x squared plus y squared, which equals to f of x equals to 0. And well, that's just a point. Do we agree with that? It's just the origin. So we can go ahead and draw that one. So that's the origin. For c equals to 4, that's x squared plus y squared equals to 4. What's that? That's a circle. And what's the radius of that circle? 2. So 1, 2, 1, 2, 1, 2, 1, 2. And let's draw the circle. Let's do the next one. So for c equals to 9 equals, so that's x squared plus y squared equals to 9. And what's that? That's another circle. But what's the radius for this one? It's radius 3. And let's draw the circle. And of course we can keep going and keep going, but I think 3 is enough. So what we have to describe here is not the surface. We have to describe the mapping here, which in this case, these are concentric circles centered at the origin. Right? And well, they're asking us to identify the surface. Well, so what do we have? So in 3D, so we have the origin for c equals to 0, and then for c equals to 4, that is 4 units up, I'm going to go 1, 2, 3, 4. It looks like there is a circle here. And then same, a wider circle. And it looks like a cone, right? It's a circular cone. Definitely not a paraboloid. Otherwise, we would have seen some parabolas in our projections on the xy plane. Okay. The last category here, and well, we're really not going to do anything about it because we're just going to mention and do one brief example to just identify what it is. And because drawing this, it's not going to be easy to do, because I mean, drawing Drawing level curves, it's easy to do because we can do like one circle of certain radius and then another one different radius and then just create a map with many of them because in 2D they're easy to draw. Now for these four category are called the level surfaces. Well, we would have to draw one surface and then another surface and then another surface. So we're barely able to draw a very simple surface. I mean, I think the easiest one to draw is the plane in the first octant when all the intercepts are positive. So imagine having to draw different surfaces like an ellipse and then outside a bigger ellipsoid and then another ellipsoid. You know, it's like, oh, again, these are going to help me. Remember this? So, let me put them together. And then I'll give you the visual. So let's describe the level surfaces for f of x, y, z equals x squared plus y squared plus z squared. Well, so we're going to set this guy equal to some value of k. You know, like k equals to x squared plus y squared plus z squared. You know, and we can give different values of k. But identifying this x squared plus y squared plus z squared, what comes to your mind when you see those three? Sphere. It's a sphere, right? Concentric spheres centered at the origin. Right? So, I mean, let me try. I know this one is not going to come up pretty. So, for different values of k, let me do one sphere. One sphere, and only in one octant. So, I'm going to get this circular shape, sort of. And outside, rather, a larger sphere, maybe. But do you see how I'm not able to, well, it's actually coming up okay. No, it's becoming a mess. If we had like 3D glasses, actually maybe we could sort of see this, you know. Have you seen those candied actually, the jawbreakers they call, or the rocaletas, those lollipops? You have different layers of flavor. So those are actually spherical surfaces in this case. Or again, think of this as a sphere. I know these are not spherical, but we can pretend these are spheres. So for k equals 5, for example, I have a Darth Vader here, right? For k equals to 4, one smaller surface inside of a surface, right? The Stormtrooper. And then k equals to 3, Boba Fett, and so on, right? Different surfaces. So in this case, we're not looking at circles, you know, or lines. I mean, stuff that we can easily draw in 2 dimensions, in 3 dimensions. So you can think of this like solids inside or outside, depending on the values of k that you choose for this. All right. So, and again, we're really not going to go really deep into this. So, applications of functions of multivariables, more than one variable. Well, again, a very common one that you have seen before, it's like that for the volume of a cylinder. Volume equals pi r squared times the height. So what is this really? This is a function v that depends on r and h. Alright, now, so you may not have seen this formula as a function, but in fact it is. It is a function of 2 variables, radius and height, not x and y, but r and h. And well, let's do a very brief example. So the body mass index, BMI, for an adult human is given by the function b of wh, w over h squared, where w is the height measured in kilograms, and the height is measured in meters. I meant to say weight, not the height. Number one, what are the independent variables right here? Weight and height, right? So in this case, W and H. What are the dependent, or if more than one? I think it's just B, right? It's B which depends on W and H. Okay, what is the domain of this function? Let's have a look at the domain. Any restrictions for any of the variables?
Square has to be greater than 0.
Has to be only greater than 0. So check this out. If we were looking at this function without any kind of context, we would have said something like H cannot be 0. Any negatives or any positive, that's fine. However, in this case, we have a context in which we are only working with positive values. So we need to redefine this as H to be greater than 0. And what about W? Even though W is in the denominator, it can take any value. But I mean, can it take any value? Just any value? Greater than 0 only. I mean, even if 0, I mean, there's no person, right? So that'll be kind of weird. So the domain here, D, is the set of all ordered pairs of the form WH such that the weight is only positive and the height is only positive. Okay, so let's evaluate B of 50, 1.5. So B 50, 1.5 equal to 50, that's the weight, and the height 1.5. So that is, we're finding the body mass index for a person that weighs 50 kilograms and whose height is 1.5 meters. And we need to square this, and this should be approximately 22.2. Okay. The question here, how can a person lower their BMI? All right, so think of the variables. So how can B be a smaller number? Number one possibility is making H really big, because when we divide by a larger number, we get a smaller number as a result. And the other possibility is to make sure that the W is a smaller number. Putting this in context would be, number one, decrease W, all right, which is possible. But I mean, what about increasing? Can I just, like, okay, next week I'm starting this new training to get taller? So it's not possible. So I think this is the only way. So of course, I mean, if we were looking at the function itself without the context, we can say decrease W, increase H, but we have a real context that we need to interpret here, all right?